Hello everyone, we're going to go over DC ripple. And going over this, we're going to cover 5 different things. First, the physical layout of 3-phase transformers. Second thing we're going to go over, how an open delta works. Third thing, what the vectors look like. The fourth thing, show and demonstrate DC ripple. Lastly, how to fix DC ripple. You do that with the choke and with the reactor. Physical layout. Everyone is aware of a Y transformer. You got 3 coils. And then what's really interesting, the vectors, when you look at any 3-phase, whether delta or Y, is plotted something like this. And you got phase A, B, and C. This is real easy to see for a Y. If you were to rotate the entire diagram around, it will look like your vectors. What is not as easy to see is when you have a delta. So a delta transformer, you have your phase drawn like so. And if you were to take this point, just physically drag it down here, and took this point and physically moved it over here, you can kind of see how that would look like your 3-phase vectors, and if you were to plot them, it would look something like that. How does an open delta work? So with a normal delta, you have your 3 coils, and you have that A, B, C. And these are 240-volt coils. And that would give you your 240 line to line. And then also what we have is when we do a center tap, you get your 120, your 240. Now, with an open delta, we only have 2 transformers, so we eliminate this particular leg. Now, if I were to take and look at VAB, if I put a multimeter there, it would equal the 240. So if I put a positive lead here, put a negative lead here, I would have that. But let's say I switch the leads, it's the same voltage, but it's in opposite direction. So VBA would equal a negative 240. If you do the same thing with B and C, you would have VBC equal 240 and VCB equal a negative 240. So what does this look like? How do we get 3 phases out of 2 transformer cans? So we have our Cartesian plane. We're going to have our one black, red, blue for ABC. So we got VAB at 240. And then we have a negative. We have a negative BA at 240. Now we have our positive 240 for BC, VBC. And then we likewise have a negative VCB at 240. And if you combine those two, the resultant is this phase here. So we have our vector A, B, and C. And that will give you that. Now what's really key though, since we don't have that and it's an imaginary, out of our bank, we only get 60%. So if it was 100 kVA total, you're only getting 60 kV out, so you don't have that use. But that is how a open delta can make 3 phases with only 2 cans. Now we're going to go over what vectors look like. So what does the vectors look like? If you remember, we have just 2 cans. So we got one leg there, one leg here. We had a center tab. We had our 120, 120. This was our 240 coil. Now, this value and this value is easy. So we have our 120, 120, and I won't get into this, but if I were to read from this point to this point, that would give you your 208. So if you were to go line to line, you would have 240. So 240, this point would be line to line, but if I went to the neutral to that point, I would have 208. So it'd be the 120, 120, and then you'll have the 208. So if you were to plot the vectors on this, you would have 120, and you would have 120, and then you would have 208. And that was what the vectors would look like on an open delta, line to neutral. So now we're going to show DC ripple. And just to bring back, we had the 208, we had the 120s, and if you were to plot these, you put an oscilloscope on this, you would see phase A, and we're going to go black, red, blue. So, but you would see phase A doing its thing. Kind of come up and go down, come up and go down, and then you would have your phase B, 120 degrees later, coming up, coming down, coming up, coming down, and so forth. And those 2 legs are at your 120. But what about your 208? So I'm just calling it phase C. It's all relative, but so phase C, or our 208 phase, actually comes way up to that 208 point line coming down. It comes way up and coming down, way up and coming down. Not the best drawing, but you get the point that from this point to this point, we have these huge gaps. and you get this ripple effect in an inverter. And that is how you have DC ripple. All right, we're almost near the end here, and the last part is how to fix this. So when you take this unbalanced part, you got the 120, the 120, and the 208. On the 208, you install a choke, which will pull the 208 down to 120. So that is we eliminate this part up here. So then you will have all three phases coming in at this level. You wouldn't get that ripple effect. But there's another part to all this, and that is, how does a VFD work? So a VFD has 3 stages. So in stage 1, you have an inverter, AC to DC. And then stage 2, you have caps that buck or boost the voltage. And then stage 3 is, how do we run that AC motor with DC? And it's called pulse width modulation. And what it really is a bunch of switches. So they're IGBTs, which stands for isolated gated bipolar transistors. And how that works is that it creates a field and by turning on and off. So it turns on and it turns off. So it creates a field and it collapses a field. And it turns on and it turns off. And it does that for each phases. So you got phase A, then you got phase B, and then so forth, and it does its thing. But I'm only going to leave the 1 so that's easier to see. And so as you get your sinusoidal wave coming up and coming down, this impacts it. So when it turns on, it's a draw on the system, and then it actually pulls the voltage down, messes it up. So it turns on, pulls it down, it releases, you get a spring up. So you're really impacting the voltage everywhere. So if I were to draw this out, you're going to get this really messy, kind of weird looking waveform, and point being, it sucks. So how do you fix that? Well, we need something to resist the change in current. And that is done by something called a reactor. It just sounds cool, but a reactor is nothing more than an inductor. So when you run the return, after you come out of the thing, the VFD, and you run it through this reactor, it actually smooths it out. And instead of it looking like this crappy old deal over here, it actually smooths out the changes in your AC waveform. Now, it's not exactly that perfect, but it gets you more to a true sinusoidal wave. So that is the 2 fixes, a choke and the reactor. Thank you for joining us today.